All right, cool. Yeah, I just had to get the recording going. All right, so I guess we'll get started. This is the day 2 for DSP. All right, so these are kind of today's goals. So we have this difference equation, transfer function, and moving from the difference equation to a transfer function. Looking at frequency response, the z-plane, it's a complex plane that we'll kind of get into. If you're taking 228 right now, it's essentially, it's a similar thing to the S-plane, but then again, I don't know how far you are in that yet. And then poles and zeros. And so this is to the right, you can kind of see what it looks like. So this is from Matlab, and this is from some of the code that I have. I just put in a random filter and then got some of these plots. So you should be able to make this, or like at least understand what's going on and get started on making it toward the end of today. So last week, the quick recap, I guess the most important points is just if a system is linear and time independent, you can view it as this black box kind of thing. You have a unit sample function that we can input. This it's a digital version of an impulse function. It's not technically correct, I don't think, to say impulse function, but it's easier than saying unit sample function. So that's this. It's just a 1 at time 0, and then, or at like index 0, and then zeros everywhere else. And when you put that into the system, you get out this h of n, this unit sample response, the impulse response. And that's the response to the shock, essentially, that is the impulse input. So you have the system there. You can summarize it by this transfer function that relates this input to any output. If you use the impulse as an input and you get the impulse response, that directly relates the input to the output in a very convenient way. But yeah, so we have this transfer function in this black box that describes this black box. We don't really know though where it comes from. It's kind of just magic. And so I kind of want to get us understanding that. One of my professors for controls would just, he was very common of just saying, you're walking along the beach and then you find a transfer function. And I want you to find blah, 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 blah. But I want to move past the walking along the beach to actually like, where do you actually get this thing from? Because they appear in, you have them in 212, 302, 314, and pretty much everywhere after, 308, they just come up in a lot of different places, and not just in EE, but this is kind of the EE side of it. So, yeah, I guess we'll start out with like transfer function. It relates the input to the output. More mathematically, if you have your input as like this x, and you have your transfer function, and it looks like multiplication. It's not multiplication, it's convolution. It's similar to multiplication, but we'll just say you convolve these two functions, which is like a fancy multiplication. And this transfer function relates the input to the output. So if your output's y, your input's x, then, just cancellation there. You should get out y as your output. So for example, like if you have a transfer function with y over x, it's 5 to 1. That means your output's going to be 5 times whatever your input is. So the multiplication analogy works here, but it doesn't work for more complex stuff. Anyway, so for an input of, if you have an input where the input is just your unit sample function, then you have a similar thing, convolve your impulse function by your transfer function. And here we have, due to linearity, it's just 5 times that. So yeah, but it's not multiplication, it's convolution. I'm not going to explain convolution. You sometimes do it in like differential equations classes and stuff. And I'll have to cover it at some point, but not today. That's not really in the cards for today. So are there any questions, or are we all good? Or I think we're good. All right, cool.
Good for me.
All right, so let's see. So you have transfer functions and this difference equation. And difference equation is basically, if a transfer function relates an input to an output, the difference equation is like a case of that where it relates the input to the output just in the time domain, or in the n index domain. So you have two cases. You have without feedback. These are called FIR. That's just like the common terminology, but it means finite impulse response. So if you put an impulse into the system, it's only going to respond to whatever your inputs are. So your output Y is some combination of you scale the first, the input, then you scale the input at the next moment in time, you scale the input at the next moment in time, and that'll get you your output. Then you have with feedback, so that's IIR, infinite impulse response. And so you have this addition of these Y terms here. So that should be a 1 and a 2, but this is still technically correct. It's just, anyway, your output though is basically a combination. I mean, if you imagine subtracting these two terms to the other side, your output is a combination of your inputs scaled and shifted in time, and then also what it used to be as the output. So for that reason, it's an infinite impulse response, because it'll never really, I mean, it's always referring back to itself recursively. And so you can have functions that just go off infinitely and never really like die out. A finite impulse response is going to stop eventually after your input signal kind of stops. So yeah, two different systems. They're both pretty cool, pretty good, useful for different things. But it's just two flavors. I mean, it's just, the FIR is just with these coefficients as 0. So I don't know if this will work actually. I'm gonna try it, but basically, let's do this. So if you have an impulse input, then it's just 1 at the index of 0. And so in terms of like a FIR system, basically we have this output is just the input plus whatever the input is delayed by 2. And so, I mean, if you look at, does the delay part make sense? Like why it's -2 and all that? I actually can't see anyone, but okay.
Makes sense.
Cool. So then, you put this in. Is this showing up?
Yes. Yeah.
Sweet. Okay. All right, so we're just delaying this x of n. And then your y is just going to be the combination of the two of them. We're not counting this because this is just x of n and n minus 2. So we're actually not looking at that. And so if you were to graph this, you'd get, it's essentially the first part, and it's going to be nothing. And then it's going to be the second part. So like that, if you want it, not in my handwriting. So from this difference equation, I mean, the difference equation will sum up kind of what you're doing on a very calculation-based kind of like way, because you have, I mean, if you wanted to, you could program, I guess, this into a computer. You could say, y equals, here's your n's, and do it kind of like we just did, and just program it in and say, okay, here's the input function. It's a 1 here, and it's 0 everywhere else. And then just shift it by 2. You could say that y equals whatever this was 2 pieces ago plus what it is right now. And you can program that in with just some for loops. And that's how computers will kind of brute force these difference equations. So it's the simplest way, the easiest way to define a system. But there are better ways for a lot of purposes to represent these. So if you look at this difference equation, so first thing is you have these delay terms. That's the n-1, n-2 here and here. And I mean, you could have additional terms. I just kind of chopped it off after the second delay. So we can rewrite it by notating delays instead. Think of them as multiplication of the original x or y by some delay. And we're going to term that with just this variable z. By the way, how's the noise outside?
It constantly sounds like a UFO is trying to land, but other than that,
right.
you could still hear you just fine.
Okay, cool.
I was thinking more like background ice cream truck.
Yeah.
Okay, yeah.
That's awesome.
Yeah, ice cream UFO. Continue.
Okay. Well, cool. So anyway, so we've got these y terms then. If we kind of substitute these yn-1, yn-2 with a z times the original y function, right? And then same thing here, this original x function times a delay of 1, a delay of 2. Well, then what we can do is we can factor out the x and y terms. So your y comes out and your x comes out. You can divide this over to the other side, and we'll just call this h. It's just the common notation. So now you have your y over your x, and all of this quantity is going to get divided underneath. So you wind up with your b's, this side, what was belonging to your x's, grouped with your what was with your y's. And so we can, just as a final thing, we can multiply both top and bottom by z squared, or whatever the lowest power is, just so that everything's positive and it's a little easier to think about. But yeah, now we have a transfer function. And so, or at least a linear transfer function. They can get pretty gnarly, but they won't for this. And pretty much any transfer function for an LTI system is going to look like this. It's just some scalar combination of how much you're multiplying and shifting the inputs and how much you're multiplying and shifting the outputs, and then relating those. If you're curious, there's no coefficient on this first term because this first term's coefficient is 1. The reason for that is because if it's over here, that's coming from your original y term. So it doesn't really make sense to think of this in terms of anything other than your output is going to be scaled by 1. I mean, if there was a different number here, you could always just divide everything by that number, and so you'd still wind up with a 1. But anyway, that's a long way to say that any system that you're relating input to output linearly can be represented by this a and b coefficients, and these are scaling the magnitudes of the different delays for the input or the output signal.
And I'm sorry, did you mention what H stands for? Or like what it's representing? What does, oh my gosh, words are hard. Like what the variable is called, I guess.
It stands for H. I don't know, it's just
Cool.
the letter that they needed to use for y over x. Yeah, I think it could have been any letter. I don't think there's a reason necessarily. Yeah. Cool. So that's your transfer function. That's kind of like where it comes from, at least in digital systems and in LTI systems. If you're dealing with circuits, it comes from the components. If you're dealing with mechanical stuff, I don't know what happens. That's all magic. So anyway, once you have this transfer function though, you can get to the frequency response of the system. So we just got this transfer function from the difference equation. The difference equation is time-based. So now we're moving kind of into frequency. And so time is related to frequency, right? But delay is frequency dependent, therefore, because delay is time-based, right? So if you change your frequency, you're going to change the delay that's happening. So transfer functions have these delay terms in them. That's the z to the negative n, or if you multiply everything by z, then it's z to the n. But because of that, they're frequency dependent. And so if you're going to evaluate a transfer function, you have to evaluate it at the frequency of whatever you're putting in. And if that thing has multiple frequencies, you have to do some cool math to evaluate that. But usually we'll just evaluate it at a single frequency at a time and then kind of sweep all those frequencies so that we can get an idea of what it does to the whole frequency spectrum. So in Matlab, easy way to do this is this freq_z command. And so it just takes the BKs and the AKs, the K is just the index, but those coefficients, and then how many points in frequency that you want your response to be, or to look like. And so it'll give you back this HF, which is just H, the transfer function, evaluated as a function of digital frequency. Remember, digital frequency goes from 0 to 1. In this case, freq_z will actually give it from 0 to 0.5. We'll see in a second why that is. But basically, it's after 0.5, everything just looks the same. So yeah, and then omega is the x-axis variable, so 0 to pi. And then I would recommend dividing it by pi, just kind of normalizing it. It makes it a little easier to look at. But yeah, so this is one way you can evaluate a transfer function, and you just get the BKs and the AKs from your transfer function. Or if you don't have a transfer function, from your difference equation. So yeah, so we'll evaluate it using freq_z. The thing is, we can't just plot omega, or W, I guess we'll call it, by HF, because it's complex. And so the response of a transfer function is usually going to be complex. So it has magnitude and phase at each point. The magnitude and phase is just the product of it being a complex number. So you can do this magnitude of HF, you can get that by just taking the absolute value of H of F, and then the phase, you can get it by using this command in Matlab, angle of H of F. And so you can see on the right-hand side, they're plotted there, the magnitude response and then the phase response. And if you look at the axis here for omega, this is a normalized kind of digital frequency. And then same thing with the phase response, actually, because this kind of goes from negative pi to pi. Divided out, it makes it a lot easier to look at. But yeah, so the way that these wind up being complex, by the way, is, I mean, it's, if you look at the B's and the A's, then you just look at that last fraction here. I mean, this is just, if the quadratic equation kind of doesn't factor it in such a way that you might wind up with complex factors. I hope that makes sense. So that kind of takes us into the z-plane. And so I guess it's useful. There's kind of, I just kind of brushed by why we're using z. But these z variables, they're representative of delay, but they're actually also, I mean, they are variables. And so we can actually treat them as such and do some interesting things with them. So if we factor on top and bottom, we can kind of find where each of these, either the numerator or the denominator, would be 0, right? And so the top, I mean, if it equals 0, then this whole transfer function equals 0. So we call these zeros conveniently. The bottom is poles, is what they're called. And those are basically, I mean, where this thing goes off to infinity if you happen to have your z equal to one of these. And so yeah, depending on the polynomial that you have here, it might not factor in such a way that you don't have complex roots. And so you might get these complex values of the form a plus a jb. So we can plot these on a 2D complex plane. And so that's what you see here. But there's kind of a weird trick, I guess, which is you have your z in a real part and an imaginary part. And so these z's can be anywhere. Your poles and zeros on this can be anywhere. But when you're actually evaluating the transfer function at different frequencies, your frequency kind of lives on the perimeter of the unit circle here. So it starts at 0 for the frequency omega, and then it kind of goes around here. And that's kind of where it's going to be. So the important thing about these poles and zeros is kind of how they relate to the perimeter of this unit circle. Because depending on where they are, that's going to affect your frequency response in different ways. So this z, you can evaluate it at a function just by looking at e to the power of j or I times 2 pi f, and that's just 2 pi f is just omega. Question. Who here feels super comfortable with the complex exponential? No. All right. Have I lost people? No? All right.
I don't think so.
Not yet.
Okay. Well, just in case, or just to like cover any gaps if they exist, I do kind of want to just really briefly kind of dive into complex. So yeah, so I mean, we're basically the way that I'm thinking about complex numbers for this, and the easiest way I think to think about all this is if you just think we're already using 2 dimensions, x and y, and then complex numbers, the reason why they're so prevalent in all of this math is that you get a 3rd dimension, but you don't need a 3D graph. So if you think about the unit circle here, you have your x and your y, and then you have this rotating value of, it's this increasing value of theta, right? And you can get to any point on this x and y with some combination of cosine of theta and sine of theta. But it's kind of wasteful to use this x and y when both of these can just be seen as like a product of, or some combination of theta. So we'll put it into this z as cosine of theta plus j sine of theta. So we're going to travel in the x direction some amount, and then the j is just travel in the y direction by sine theta. And so an easy way to do that through Euler's identity is just e to the j theta, and that gives you both of these points. It's the cosine part, the x amount, and then your y amount, or just rotation and then going out by a certain radius or certain distance from the origin. Cool.
Good.
All right, so then we get to plotting these zeros and poles just to make it, complete. So if you plot them on this complex z-plane, thankfully Matlab will do that for you. So if you specify your bk's and your ak's just as a list of the coefficients, or as an array of the coefficients, it'll spit out this nice plot for you. It doesn't get labeled with my cool annotations. But yeah, so you have zeros represented as just an O, you have poles represented as an X. And if you think that, okay, so like this is your, Z is kind of evaluating at a frequency. It's E to the J 2 pi F. So you're just rotating by a certain amount of however much this 2 pi F is. Well, if 2 pi is a rotation around the whole circle, right? That means that when F is equal to 1, we're going to get all the way around. So that means if F is equal to half, we should get halfway across the circle. We should get to the other side. So that kind of gives us some landmarks. If this is 0.5 of F, that means that F here is going to be, your frequency is going to be 0.25, and here's your frequency of 0. And so as you increase your frequency, you're kind of going to go around this. And depending on what your sampling frequency is, that's going to relate to different physical sample values or sample frequencies. But whatever your sample frequency, whatever your sample frequency is, like this is where 1/4 of that will kind of live. Because the digital frequency, remember, is just normalizing the analog frequency. So as your frequency moves through here, it's going to be convolutionally multiplied by whatever the transfer function is. And so the thing that's closest to it is kind of what's going to dominate. So if you think of, the zeros are on the top of the transfer function, right? And then the poles are on the bottom. So anywhere that you have a 0 nearby, it's going to basically multiply by something that's closer and closer to 0 on top and something on the bottom. And then same thing, if this frequency happens to move near to a pole, it's going to multiply, or it's going to divide by something very close to 0. And so it's going to go off to infinity. And so your magnitude response is going to kind of do the same thing. So zeros, wherever we place them on the unit circle, that is when the frequency that we're evaluating crosses that point, we're actually going to see the magnitude drop to 0. And so you can see that in the plot here. You have these two zeros at 0.15 and at 0.4 something. And that's as a direct result of these zeros here and here, 0.4 something. And so the reason why this pole zero diagram is so useful is just because now by looking at this, it kind of gives us an idea of, you don't really know what AKs and BK coefficients are going to get you a certain response that you want. But it's very easy to look at this pole zero map diagram and just say, oh, okay, I want no response. I want a very low frequency response down at low frequencies. So I want a low magnitude. So we'll put a bunch of zeros down here, and that'll pull everything down at these frequencies. And then as we get to the higher frequencies, oh, maybe, well, I don't want that. So I'll remove the zeros here. So it gives you a way to just place zeros just by looking at this thing. And then from those poles and zeros, you can get back your BKs and your AKs, and then you can eventually get to a difference equation if you want that. So pretty powerful tool. It allows you to construct kind of whatever filter you want, more or less.
So by placing zeros, does that mean that you're rewriting the equations so that those zeros end up where you want them? Or how are you putting the zeros there?
So these zeros are found by factoring this
okay.
Transfer function, right?
Yeah.
So if I start out by saying, okay, I'm going to have a 0 at like 2 and 3, right?
So you can
just FOIL it out.
Okay.
And then whatever you get back as your coefficients, you're only going to get one coefficient for z squared, one for z, and one for z naught, right?
Makes sense.
And so you can work your way kind of between any of these forms if you understand kind of like the relationship between them. So yeah, you can specify these and then just multiply it out. That'll get you your coefficients, and now you're back to a transfer function. If you want to go from a transfer function to the difference equation, multiply this over to the y, basically do the inverse of what we did before. Multiply this to the other side, multiply the x up top again. You end up with a y on one side and x's on the other. And then you can kind of work your way backwards through here, and you'll eventually wind up at a difference equation.
Cool. Okay. Sounds good.
So,
thank you.
Yeah, that was a good question. So this is kind of today's project, is to create the tools to view a filter's properties. So we're going to want something that lets us plot the output of a freq-z filter frequency response. So freq-z will give you this magnitude and this phase, and it's just a list of numbers as magnitude and a list of numbers as phase. We want to turn that list of numbers into something like this. And if you do that manually every time, it's going to get really, really tedious. So it's convenient to just make a function that'll put two plots the top one with the correct, this x-axis isn't going to change. The y-axis, Matlab will automatically scale for you anyway. Same thing with this digital frequency, it's the same axis. So makes sense to make that. Then you want to be able to get the filter's response from your BKs and your AKs, and your filter's response from zeros and poles. Now, because zeros and poles directly relate to BKs and AKs, if you can make this function, then making this function is literally just translating these zeros and poles, multiplying them out to get your BKs and AKs and feeding those into the function that you create here. So they're really the same function. This one's very short once you have this one working. And so you'd want these filter response programs or functions to output your plots of, they should ideally give you probably a zero and pole map so that you can visualize where those things are. The frequency response, which is just that, with a phase component ideally. And then unit sample response is always good to have as well, just to see kind of what the time domain version of this is. So I put like some starter template code into the Google Drive, and I can put a link in our Slack to that if you don't have that or something. But yeah, basically kind of outlines like what needs to be done. And then it just, has sections for you to fill in. It's also a little bit useful just because there are certain things that you need to do, like you need to make sure that your AK and your BK coefficient arrays are the same length for when you're doing this stuff in Matlab. We don't have to worry about that when we're doing it, computers do. So I took care of like that kind of stuff so that you can kind of just get to the other stuff that you should be able to fill in, maybe a little confused, but like should be able to fill in with what's kind of contained in this workshop today in combination with last week. So yeah, I guess, are there any questions, or should we get into the...
This is just general for like everyone else, but like, does everyone have access to MATLAB or know how to do that?
I have MATLAB. I'm still just working on the basics of learning it.
Okay. And then how about you, Lucas?
I understand I got like SolidWorks from the Cal Poly like download stuff, so I assume it's something similar for MATLAB.
Yeah, you can download MATLAB through that same process of like the technical requests. Also, are you in the College of Engineering?
Yeah, I'm in electrical engineering.
Okay, so you should be able to log into, I don't know how it's, I've heard it said like Cengwitz or like CENGWTS. So like the College of Engineering, they have like a remote desktop login if you don't want to wait for like MATLAB to fully download right now. Or you just don't want it taking the space on your computer or whatever it is. So you can remote access to that. And I'll send a link to the Slack too.
When I downloaded MATLAB, it was really easy. You didn't even have to do a technical request. They have a page for it that basically tells you what your login will be, and you can just log into the MATLAB website and download it.
Oh, really?
Yeah, that's how it was for me like 6 months ago. Maybe they've changed things, but it was very easy.
Pretty similar. I just did it recently. Yeah, when you download it, it'll ask you what kind of plugins you want. You could take the nuclear approach and just select everything. But for this, what you'll definitely want is either DSP. It'll ask you like toolbox that you want. And you'll just check either DSP or audio. I think it's like audio manipulation. I don't know. It's something like that. But there's a couple that all contain whatever functions we need. So yeah, I guess if you guys are kind of new, some of you, to MATLAB, what I was thinking is like after this, I mean, now we can kind of like break into kind of individual work. And then I'll kind of like try and help out as much as I can, or like, with whatever it is. And I'll probably be coding these at the same time just to get like an official version out. And then, yeah, if you don't finish it today or something, I mean, you can work on it throughout the week. If you want to hit me up with like questions or something, you can ask me and be like, you know, why is this not working, or how is this supposed to work? And then I'll also post my version, my final version, into the Google Drive. So if you don't get it working, or you're just like, geez, I really don't understand how this is supposed to work, it'll give you something to look at, so that you can kind of either like work backward or at least just be caught up. So does that sound good?
Yeah, I appreciate it. That's cool. Don't worry about me too much because I'm pretty much totally new to this. I've just always kind of been looking at AES and wanting to hop in and like see what you guys do and stuff. So I'm a little bit over my head, but I kind of like to do that and then just see, kind of get inspired of what I'm learning, you know, Calc 4 and everything for in the future.
Cool.
Absolutely.
All right, sweet.